Welcome to Study Loop.
This is the answer to Chapter 14, problem number 3 from the Smith Organic Chemistry textbook. And this problem asks us how many 1H NMR signals does each compound show? And so remember that each different type of hydrogen, each different proton in a molecule is going to give its own signal. And so the number of different types of hydrogens is going to determine the number of signals. And so for A, there's only one type of hydrogen. So all 6 of these protons are equivalent. And so there's only going to be one signal for all 6 of them. So then for B, we have 2 types. So we have these CH3 types, if you will. So they're going to give a single signal. And then the 2 protons here on the central carbon are also going to give a single signal. So that is 2 signals. So 2 different types of hydrogens. So then for C, we also see 2 different types of hydrogens. So for C, again, we have the methyl protons on the ends, and then we have these equivalent methylene protons inside. So we will also get 2 signals here for C. Okay, so then for D, again, we're only going to get 2 kinds of signals. So we have 6 of these methyl group protons on each side. So they're going to give a single signal, all 12 of those protons. And then we have these 2 methine protons in there, so just CH. And so they're also going to give a signal. So once again, for D, 2 different kinds of protons, 2 signals. Okay, so then E, each of these is a different type of proton. So looking at B, C, and D, what we saw basically was that there was a plane of symmetry through the middle of each molecule. So we could divide each of these molecules neatly in half, and that's how we would. That's why the protons to either side were equivalent. So that's not the case in E. There's not a plane of symmetry here because it's an ester, and so the right side is going to be different than the left side. So these protons are unique. These protons are unique. These protons are unique. And these protons are unique. And so the end result of that is going to be 4 signals. So 4 different types of protons. They'll each give their own signal. So 4 NMR signals. And so F is a similar case. So I will just highlight each of these are different. And then these 6 here, so the 2 methyl groups, are all going to be a single signal. So again, 4 signals for F. Okay, and then so looking at G, what we see in G is that we'll get a single signal for this methyl group. So for these 3 protons, and then the presence of this chlorine means that each of these CH2 groups is different, because the first CH2 group will be adjacent to the chlorine, and then the next one will be one away from that, and then one away from that, so on and so forth. So the answer here is actually going to be 8 signals. Now, in real life, would you be able to distinguish all 8 of those signals? Probably not. It would probably all run together on the spectrum. But for the purpose of this problem, you would there should be 8 distinct signals. And if you had a powerful enough magnet, you probably could get those to resolve. Okay, and then so for H, H is going to be a similar case. So even though there are these 2 CH2 groups, one of them is immediately adjacent to this oxygen in the alcohol, and the other is not. So we're going to have a signal for these 3, a signal for these 2, a different signal for these 2, and then the alcohol proton is also going to give rise to a signal. So the answer to H is once again is 4. And so that's the way to approach this problem. We just need to identify how many different types of protons are in each of these molecules. And then each different type of proton is going to give rise to its own signal. So we count the different types, and that's how many signals we should expect. And that's the answer to chapter 14, problem number 3.